Welcome back to the Qiskit Global Summer School. I'm your host, Nick Braun, a quantum researcher at IBM. In this final session, good job for sticking with us, by the way, we're going to be talking about mitigating noise in actual quantum hardware. We have some sort of quantum algorithm we wish to run. We have to map that to a physical device, and in this lesson, we're going to discuss the details and the code of what we talked about in the previous session. To review, we're going to be talking about things in kind of three different buckets, the way I like to think about it. The first problem is of qubit mapping, where we need to be smart about the qubits that we use for our algorithm. That consists of routing and layout. Then we'll talk about error suppression, or using physics to reduce the errors in our system. Techniques we'll talk about there are parallelization, pulse scaling, dynamical decoupling, polytwirling, and measurement error mitigation. And then lastly, we'll talk about error mitigation, which is ways to analyze circuits in multiple ways and extrapolate to the case of zero noise. This is, for example, zero noise extrapolation or probabilistic error cancellation. And the first two we'll talk about transpilation mainly. The transpiler is Qiskit's way of taking an abstract circuit to an actual circuit that can run on quantum backend, but there's many ways to do that, and we want to do it in the smartest way. Or error mitigation, where we can transpile in different ways in such a way that we can model the noise and reduce that amount of noise so that we can get a better estimation of an expectation value out. And these are all coming from different repositories because a lot of them have to do with very specific things about Qiskit or the way the hardware is run. So for example, there are a couple packages called Mapomatic we'll use for layout from Qiskit Partners, and M3, which is matrix-free measurement error mitigation. These are both pip installable, and we reviewed last time. We also have a Qiskit research repository, which is on GitHub and can be cloned and installed locally. And we have Qiskit IBM Runtime, which is pip installable and consists of these error mitigation methods, which are accessible via the resilience level flag. Qiskit Research in particular was detailed in episodes of Nick Knows Season 2, and the Qiskit IBM Runtime is detailed in Coding with Qiskit Runtime, which I also did. Let's talk about qubit mapping. I will break this up into two separate cases because although they're entwined with each other, I think it's better to think of them as separate functions. So we'll talk about routing first. So why do we care about routing? Well, we have a limited connectivity on our quantum computer topology, which is okay because we can always introduce swap gates which move the quantum information around. And that process of adding swap gates to move our abstract circuit of arbitrary connectivity to a physical circuit with limited connectivity, we refer to as routing. Now, if we look at what one of these swap gates are, we can decompose this into something that actually executes on the quantum hardware, and we can execute a swap gate as a series of 3 C-naughts. I believe my colleague John talked about this last week. However, if we go to our backend we're going to be talking about, IBM Q Kolkata, we look at our best C-naught that we have, it has an error rate of about 0.4%. And so if each of those C-naught gates are going to be 0.4%, then when we go back to our swap gate, we see we incur at least a 1.2% error in doing a swap gate. So in effect, the first thing we ever want to think about when we execute a quantum circuit on real hardware is how do we eliminate these swap gates because they will be the largest source of error. And we can do that through effective routing, and we can do this algorithmically as well. So when you employ a routing algorithm, in fact the one that Qiskit uses for optimization levels 1, 2, and 3 is called the Sabre algorithm. The routing algorithm is an NP-hard problem in general. However, this stochastic algorithm is extremely fast and allows one to find relatively quickly the optimal solution or an optimal solution. It can be run multiple times so that you can pick among those solutions and find the best one. In fact, it's been rewritten in Rust so that it's multiply parallelizable, and it actually runs pretty quickly and should be scalable up to 1,000 qubits or so. So IBM Kolkata is the backend that we want to route to. Let's find a test circuit that we can examine. I'm going to use the 5-qubit GHZ state, which is created by either of these circuits, and there's a reason I did this in 2 ways. Firstly, well, in either case, I need to do a Hadamard to the first circuit, but in the first way on the left, I'm going to use a waterfall structure, and I'm going to do a C-naught between that qubit 0 and all the other qubits in order to generate that 5-qubit GHZ. Alternatively, I could be a little bit smarter, knowing that I don't have all-to-all connectivity. I might think it would map better to my backend to do a Hadamard on qubit 0 and then a staircase structure of CNOTs between qubit 0, 1, then 1 and 2, then 2 and 3, and 3 and 4. And that would be correct. The circuit on the right scales much better maps much better to our hardware than the circuit on the left. And in fact, one of the things that I like to tell people is that when we're talking about these routing and layout problems, these are basically subgraph isomorphism problems. The transpiler does not know what you're doing quantum mechanically. If it did, it would be, as good as a quantum computer at least, and we know that it's not. So when we lay these things out, we need to be a little bit smarter. And so although the circuit on the left and the circuit on the right are exactly the same as far as quantum mechanics are concerned, from a graph theory problem, which is what is being optimized, they are completely different. In fact, it is like a star-like structure assumed on the left, where the qubit 0 would be in the middle and all the other qubits would be emanating from it, versus a linear kind of topology where we go from one to the other on the right. And just as an example, because I know the one on the left is going to be bad, we're going to use that as an example. So what we're going to do is code up that circuit in Qiskit. So I'm going to import the quantum circuit, 5-qubit register. I'm going to do a Hadamard on qubit 0, and then do CNOT between qubit 0 and all the other qubits. And I can draw that, and I see the same circuit we had before. Now what we're going to do is we're going to import a preset pass manager, and we're going to look at the stages like we talked about. The pass manager is staged now. We're also going to import the IBM provider so that we can run this on an actual backend. Note that Qiskit IBM provider is the way that the IBM backends are accessed now, and the old IBM Q method has been deprecated. We're going to get our backend IBM Q Kolkata, and we're going to generate our preset pass manager where we're setting optimization level equal to 2, and the backend is IBM Kolkata. And then we're just going to look at the layout function of this and see what happens when we do that. And what we get is we're going to have a Hadamard on qubit 19 now, the physical qubit 19, from abstract qubit 0. And we're going to have CNOTs emanating from each of those qubits 19 to qubit 16 to qubit 20 to qubit 22. But alas, qubit 14 is not attached because we have at most 3 qubits attached to any other qubit on the heavy hex lattice, which you can read about in the most important graph video, most important graph in the world video, which I talked about earlier. Because qubit 14 is not attached to qubit 19, we have to do a swap between them. So we're going to suffer from at least one swap. From a graph theory perspective, you cannot do better than adding this one swap, but we know if we laid it out smarter, we would need no swaps. But we want to handle the case where there are swaps anyway. Okay, so thinking about routing again, this has been now routed to a topology. Now, even though I've assigned this to certain qubit numbers, this would work with any set of qubits that had the same topology. So I actually don't need that information about which qubit it's been assigned to already. But it has been laid out for me because that is how the algorithm currently runs in Qiskit. Really, any of these abstract qubits that had the same topology would work. Basically, I need the middle qubit attached to 3 qubits, and then one of them attached to qubit, one of those other qubits, where I will add the swap. Now that we've successfully routed the circuit, we'll consider the problem of layout. In order to approach layout, we need to figure out what the best qubits on the actual circuit are for using our algorithm. In that way, we need to convert the circuit into something that is already in the basis gates so that we know how to, we know what the errors are for the gates we want to do, so that we know how to reduce those set of errors. So for example, before doing this, we want to convert that Hadamard to an RZ, a square root of x, and an RZ. The RZs, of course, are perfect. They have 0% error. The square root of x's are less than 0.1% error. We know each one of these C naughts is going to be at least 0.4% error. And we know the swap turned into 3 C naughts here. So now that we've decomposed this function, we have this layout that came from the layout pass of the stage pass manager. What we want to do is lose that information. And we want to then score this layout along any different layout we can have on the IBM Kolkata itself. So in order to do that, we're going to do some steps that we pull from the Map-O-Matic function, which is pip installable I mentioned earlier. The first thing we're going to do is we're going to deflate the circuit, which is going to remove all the physical qubit information from that circuit so that it does not correspond to qubits 14, 16, 19, 20, 22 anymore. It's going to go back to the abstract circuit. And then what we're going to do is we're going to look at every matching layout of those 5 qubits that is compatible with that swap network that was routed in the previous slide. We're going to look at the error rates of each of those qubits in each one of these circuits that would actually be performed for every given configuration. This is in general an NP-hard problem, but we're using a stochastic subgraph isomorphism program called VF2 layout, which Map-O-Matic is a wrapper around. Given each one of those layouts, we're going to score them by evaluating them by essentially multiplying the fidelities of all the operations in the circuit together and inverting that to get a kind of infidelity score, where this is not a rigorous definition of how well the circuit should run, but it's kind of a ballpark idea of how well you can do. And it's good for picking the best qubits on a device, for example. For these scored layouts, they are sorted in order from top to bottom. So the first one is going to be the best layout. And in fact, when we run this on IBM Q Kolkata, we see the best layout is actually 7, 4, 1, 2, and 0. So what we can do with that information is we can put that back into the transpiler by specifying those qubits as the initial layout when we retranspile that backend and consider it mapped, which is why we call it QC sub m. And so when we actually map that circuit, we see our abstract qubits Q0 through 4 go to qubits 0, 1, 2, 4, and 7, with qubit 1 being the middle one, because that is attached to qubits 0, 2, and 4, and not attached to qubit 7, so we have to insert the swap there. And when we do that, we can calculate the infidelity score, and we can compare it to other infidelity scores. So we can look up the error map. For example, on the IBM Quantum Services page, we can get all these errors, but what we're going to do is deal with them inside of the backend framework in Qiskit. And for example, the infidelity score here we get is 0.023, which is what we get from redoing this. If we kept the original layout of 14, 16, 19, 20, 22, we would get 0.024, which isn't much worse. It's a little worse. However, the previous routing algorithm knows nothing about what qubits it picked. It picks them at random, and so if it randomly picked the wrong ones, we could get up to a 0.1 infidelity score, which is roughly 4 times worse. So by being careful about the qubits we pick and trying to find the best ones on the device, since we're not often using all 27 qubits, we can use these subgraph isomorphism problems to route and then lay out the circuit in the best way possible. Another good thing about this is the cost function is user-defined, so you can override this cost function and indicate your own, and you can try to use this to figure out how well your circuit might run, or compare it to other circuits, or to see how much you improve the expected fidelity from this process of being smart about mapping the qubit problem. The next thing we'll talk about is error suppression. So this is the kind of next bucket. And we'll talk about what is the physics of the devices and how do we improve upon that. And one of the ways we can improve is through parallelization. So for example, if you've done variational algorithms before, which were talked about on the previous day, we know we can build an ansatz, which is a fancy German word for guess, out of a series of single and 2 qubit gates using the algorithm 2local, which combines single and 2 qubit gates in an algorithmic way. For example, in this example, we'll use the Y rotation and the ZZ rotation, and we'll employ this on IBM Q Kolkata as we have been. And what we can do is we can try and be smart about this and enforce a linear entanglement, which will just try to encode the ansatz by entangling qubits that exist along a line. In that way, we know we're not going to add any swaps. For example, if we did all-to-all entanglement, there would be many swaps because of the need to move quantum information around in a limited connectivity. So what we have here when we do a linear entanglement is we have a staircase type structure where some of the staircases kind of tumbled around a little bit just because of the actual connectivity of the numbered qubits. And we see them happen in kind of a serial way, where, for example, the ZZ happens between 0, 1, then 1, then 2, then 2, then 3, 2 and 3, then 3 and 5, then 5 and 8, etc. However, a lot of times we know in ansatz we don't care about things executed in serial. In fact, we could think about them happening in just layers where we do ZZs on half the qubits and then ZZs on the other half of the qubits, followed by the single qubit rotations. One of the things that's interesting about this is that these ZZs actually commute with each other. So quantum mechanically, the circuit on the left and the circuit on the right are exactly the same thing quantum mechanically. One of them has a staircase structure which operates in serial, the other one has a brickwork structure. The important thing to think about is the staircase structure is that it's going to take a longer time to run because you're doing everything in series. And so that offers the qubits more time to decohere while other things are happening to the other qubits. So in that sense, in reducing the amount of time, you're going to be less susceptible to decoherence, which is what is offered by the brickwork structure. However, one thing to be concerned with is the brickwork structure could feature crosstalk, in which case the qubits that are being operated on have some sort of extraneous effect on the qubits that are adjacent to it, for example, and that could be bad for certain algorithms. For example, the ansatz design of 2 local, usually you would not care about crosstalk so much because you have the ability to optimize with the classical optimizer, so any kind of coherent errors could be washed out, quite possibly. However, if you're doing a quantum simulation type algorithm, any kind of coherent crosstalk is going to introduce errors that can ruin your algorithm. So it's very important to be careful and think about what you're doing when you're approaching these techniques such as parallelization. For example, we have some work on crosstalk that was done in conjunction with Princeton University where we characterized these kinds of things. For example, we can look at 2 adjacent pairs, Q0 and Q1, and Q2 and Q3, and we can measure the amount of crosstalk that happens between those qubits. And we see that this pair actually has a high amount of crosstalk. We can do this by looking at the difference between simultaneous and randomized benchmarking. So for example, we could separate these gates in time. By doing them at different times, we have less crosstalk and they're less affected by each other. However, then we might have a long duration where we experience a lot of decoherence because now everything takes longer to do. So what this paper actually tried to do was come up with a strategy for transpiling these circuits in that they are crosstalk aware and the gates are moved into situations where you can have a minimal amount of crosstalk and still not take a long duration. So this is an interesting problem which is still being actively researched today. And this can also have an effect on the kind of algorithm you might be looking at. So for example, you might expect that qubit operations were not good between adjacent pairs. But what the authors also found was that even gates that were 2 qubits apart were being affected by the crosstalk. And this was done on devices that were prior to the heavy hex lattice. And they were characterized explicitly using these benchmarking techniques to monitor the crosstalk. And like I said before, depending on the algorithm, you may or may not care about crosstalk. It can be, variational algorithms can be immune to it, so you might not even care. You might be much more susceptible to decoherence, for example, and so you might want to minimize them even with the added crosstalk. Another way we can do error suppression is something that I personally worked on a few years ago, where we have say a quantum simulation algorithm given by this Hamiltonian. It's not really important what Hamiltonian this is. The only thing you really need to know about it is that we're doing YX interactions, where YX refers to the poly Y tensored with the poly X, as discussed in the previous lecture. And when we want to map this digitally to an actual backend, we might look at this and analyze it as I typically would, and I'd see C naught here, and I'd see each one of those would have about 0.5% error. And I'd look at the controlled Z's, and I would see that that's actually a C naught plus some single qubits, which will have error. And I can see this C naught that does not exist on the actual architecture, so I need to decompose this with a swap as well, which is a lot of error. However, at the end of the day, for these quantum simulation algorithms where I just need a y-x interaction, the angle I need a rotation about the y-x axis in is about pi over 10 to pi over 3 for this particular simulation. That is going to be a lot less than the pi rotation I get from doing each one of these digital decompositions, because each one of these C0s is locally equivalent to a zx rotation of pi over 2. And knowing that, we can think about redesigning this circuit so that we actually efficiently use the cross resonance in order to just generate the zx rotation that we need and turn that into a yx rotation. So for example, each one of these yx interactions is going to be mapped digitally to the back end by putting down a C0 between two qubits, a y rotation by an amount theta, and another C0. So in this way, we have an angle theta, which is relatively small, and it's being mapped to the gate that has the least amount of error. Whereas each one of the C0s is a pi over 2 rotation in the 2-qubit Hilbert space, and we always have 2 of them for an effective pi rotation. So if we were to write this down into the atomic units, which consist of echoed cross resonance, then we can scale the duration in such a way that we can just generate the angle of rotation we need for this algorithm. And in particular, each one of these atomic units is an echoed cross resonance, and when we add these single qubit gates before and after, that becomes the same thing as a yx theta, which is above. And that yx, in fact, consists of the zx rotation we get from cross resonance, added with a couple x rotations in order to generate that yx of theta. Here, what we've done now is we've mapped that theta, which is relatively small, onto the 2-qubit gate that has more error. So we could expect, and indeed observed using process tomography, that we were able to get higher fidelity, especially for smaller angles, because we're scaling the amount of error that is actually occurring in this operation. Quantum mechanically, these are both exactly the same. They're both yx of thetas, but the way you implement it gives an additional improvement of the scaled pulse implementation, especially around the angles from about pi over 10 to pi over 3. You get maybe about a 50% improvement. You'll see at the top that this improvement also goes away as the angle gets larger and larger, because when you get out to pi, you're doing the same amount of 2-qubit rotation as you were doing in this digital implementation, and hence you're occurring the same error. So in this way, without doing any extra calibrations, we're able to lessen the amount of cross resonance and hence lessen the amount of error, which varies about linearly in the angle that we want to achieve. And because quantum simulation algorithms often have small angles, this is a good application for quantum simulation type experiments. For more information on quantum simulation, see my earlier video on Qiskit Nature. In the Qiskit research repo, we also have the ability to do this now with one line of code. So which was the scientific piece of research 2 years ago, now is just one line of code that you can import and use yourself, because all the pulse level information is taken care of for you. So we import the scale CR pulses from the Qiskit research repo, and just by inserting the circuit that we have that has these RZX gates, or something that can be turned into these RZX gates, inserting the backend and any parameters we might need to bind to that backend, which are necessary for attaching the necessary pulse information as pulse gates. Speaking of pulse gates, you can see my video on long live Qiskit Pulse, rip Armonk, long live Qiskit Pulse, where we describe what pulse gates are. We can attach these pulse gates for you, and you don't have to think about them at all, which provides the backend the information you need in order to execute these. So if we put these two together, we can try to do pulse scaling with the two local ansatz and see what happens. So just to remind you, the parallelization, what we're going to do is change the staircase structure of a circuit to a brickwork type structure. And if we were to schedule that and look at the pulses and just look at the cross resonance ones, the yellow pulses as mentioned in the previous lesson, we would see all these yellow pulses happening in a row, and things take a long time, as compared to the bricked and pulse scaled version, where we have parallelized everything and we have additionally scaled the pulses, so we have much less cross resonance that we actually need to do. So the x-axis is time, and these are equal between both of these, and you'll see that the one on the right has about 1/6 of the duration, so you might roughly think that it will run with 6 times less error. You know, everything is kind of ballpark here. And so you get this kind of improvement just using these two error suppression techniques. The next thing we'll talk about is dynamical decoupling. There's a great review called the Quantum Engineer's Guide to Superconducting Qubits that you can read down here. But basically, your qubits are going to be susceptible to a bunch of noise. And that noise has a power spectrum given by this graph here as a function of frequency. And usually what we're looking at is low frequency, kind of 1 over F type noise at frequencies at which we can have control solutions, and these control solutions are often done by dynamical decoupling. We can, in effect, engage this control solution by building a filter function by doing a series of pulses. So in some way, you can think of dynamical decoupling as an insertion of pulses during the idle time in which a qubit is not being operated on. It is just suspect to this noise spectrum. And you are putting a filter function over that noise power spectrum in a way such that you can null certain frequencies of noise. So that has an improvement on the dephasing of your qubit, for example. Another way you can think about this from Nick No's Season 2 is that you get some broadening due to the phase fluctuations, which comprise dephasing, into an envelope which spreads out from the state you might want it to be in, and you can just flip that qubit such that that noise spectrum will then refocus itself. So in a simple way, the echo pulse is the simplest type of dynamical decoupling, and it allows you to do some simplistic refocusing of error in such a way that this is similar. So for example, you basically would like to add dynamical decoupling sequences, which are these sequences of typically like X or Y gates, but these are varied and numerous, and there's a lot of different ones you can employ, into the time in which your qubits are actively trying to maintain a superposition, a coherent superposition, but not when they are idle. So for example, in the 7-qubit GHZ state, in the lower left, all the qubits are still in the ground state because that's where they start, and we don't want to do dynamical decoupling because there's going to be an inherent gate error for each one of these operations, and those are just sitting in the ground state, so we can just leave them there. Whereas on the upper right, these qubits are idle and coherent, and therefore they're going to be susceptible to noise, and that's where we want to add dynamical decoupling so that we can prevent the dephasing from occurring. So as an example, we can take a circuit and look at it with the timeline drawer from the Qiskit.visualization tool, and we see all the cross resonance, which is the longer operation, which is what's happening in this kind of GHZ circuit, and then we see the idle time on the upper right. We can insert dynamical decoupling sequences. In this case, we're using the XY4 dynamical decoupling sequence, which will insert XY, XY, which, when you compose them together, add up to the identity as if you were doing nothing on the qubit. So circuit-wise, quantum mechanics-wise, it's the same operation, but because you're implementing it differently, you're flipping the qubit around in such a way that will reduce the dephasing. So you're just running it in a kind of different way, where the sequence has been added for you with a specific timing scheme. Well, in this case, the timing tau between each pulse, there's a timing tau between each pulse and a timing tau over 2 between the entangler and the first one, and the last one and the measurement. This can be done with another tool from the Qiskit research repo called Add Dynamical Decoupling, where you add the circuits that you want, the backend that you want, the sequence that you want, in this case XY4, and if you have some pulses that are not part of the basis gates of the particular backend you're using, you can add the pulse calibrations that will add the pulse gates that will allow you to execute what you want. As we discussed in the Coding with Qiskit runtime video, we can also add dynamical decoupling by setting optimization level equal to 1, 2, or 3. Also, we'll need the resilience level to be 0 because we do not want to learn the noise in that case. We want to do the bare error suppression that dynamical decoupling offers. The next thing we can do is polytwirling. So say we have a noisy gate. In our systems, the C0 tend to be the noisiest gates. So we associate with it an error map, which is kind of an abstract thing we attach to the C0 that describes the error generated by it. If our error map was equal to the identity, in which case we have no error, we could think of writing our circuit in different ways using random polys, for example. So we could add some single qubit gates before and after the C0 But in the effect, quantum mechanically, it would still be the same as a C naught. Basically, what we're doing is we're executing this in different ways, and in this way, doing this with Pauli gates is known as Pauli twirling. We can look and see how this behaves, and in effect, what we're doing by twirling over these gates is we're taking any kind of coherent error that exists in our system and turning it into a stochastic error. And the good thing about doing that is that we can average over stochastic error. We cannot average over coherent error because it continues to add up in a coherent way. But stochastic errors we can average over and get a better result. So in this quantum simulation result from my colleague Yunsuk, who just had it published in Nature Physics, we can see what that looks like. This is a quantum simulation type algorithm. And in quantum simulation type algorithms, such as quantum phase estimation, you can derive the answer from the frequency of oscillation. So what happens is if you have an extra coherent term, you're going to be affected and have an incorrect incorrect frequency of oscillation, say given by this green curve where there was no Pauli twirling executed. And that frequency of oscillation could be faster or slower than the actual one that is ideal, which is given in the dark gray. So just by adding some instances with some random seeds and adding these into the circuit and averaging over the same number of shots, you're able to average over that error and quickly get back to the same frequency of oscillation. Also, the number of averages you'll need will also vary depending on the kind of algorithm you're running, but for this case, about 8 instances was all you really needed. So we can see them this way, by adding this Pauli twirling, we're able to get the same frequency of oscillation and hence the same result that we would get in the ideal case. And this is, of course, very important for quantum simulation type algorithms. This can be done with another method from the Qiskit research repo called add Pauli twirls, where we add our circuits, we have the number of twirls we want, we can seed that, and of course we can transpile these added Paulis. One thing about this Pauli twirling that is nice is that we can add each one of these Paulis and we're not actually getting the effective error from adding those gates because we transpile those with all the other single qubit gates around it. So in that way, we're still going to have a maximum of 2 square root of x pulses that we're physically doing with microwave pulses on the actual device, so we get the same amount of error. So this kind of comes, in a sense, for free in cost, unlike dynamical decoupling where you're actually adding and doing the pulses themselves. This doesn't require any extra computation, but you might need to run circuits in batches because you will be running over different circuits, which you will average together in the end, even though the number of quantum resources, such as shots, is conserved. Another kind of error suppression technique we can have is measurement error mitigation. Now, in order to understand measurement error mitigation, we can understand the process of measuring a series of qubits to get their classical bit strings out as a process matrix we call an A matrix. And that A matrix just corresponds to what are all the preparations of the qubits in the quantum computer we could prepare, and then what are all the measurements we get out. And ideally, you would get out everything that you prepared, you would get a corresponding measurement that was identical to that. But in practice, there will be some noise, some crosstalk that gets introduced in the system so that you might measure something other than what you intended to prepare. And we call this process the A matrix, which is actually classical. And what we seek to do is basically invert this noise process. So as a matrix, we can invert it, but in general, those kinds of inversions are very expensive. So what we do with the matrix-free measurement mitigation done by my colleague Paul Nation is we calculate the reduced A matrix, which makes it small enough to we can do an efficient LU decomposition on it. And so we can turn a very large matrix problem into a relatively small matrix problem and invert it. And we can do this with the M3 package. We use this M3 mitigation tool where we create an instance of this mitigation for the back end. We get the calibrations which actually run an experiment to prepare the needed preparations of the quantum computer and the measurements of that quantum computer, and then store them in this M3 mitigation class. And then after you've done that and after you've run your job, you just apply correction, class to it, and it knows how to change your results into a series of quasi-probabilities corresponding to the improved measurement results, where they're not actually probabilities because they've been mitigated. Of course, you'll need your layout because that will depend on the, that should be the same as initial layout. That will depend on the qubits you're actually using so that you can extract the appropriate error information from. So this has a small amount of overhead, so it's not exactly suppression, it's kind of mitigation, but it's a relatively small amount of overhead. And there's other ways you can approach this too, such as using resilience level 1 in Qiskit runtime. It's going to do measurement error mitigation, but using a different technique called the twirled readout error extinction, which is done by my colleague Ewat. And these techniques, because they are characterizing the system and they are relatively kind of classical, they generally work and you can get improved results. However, there are certain kinds of algorithms such as quantum volume where you are not supposed to apply these kinds of techniques. So error mitigation now is going to get us into the realm of analyzing the circuits in different ways in order to learn about the noise of the system so we can ascertain or extrapolate what the values of the circuit should be in the case of no error. This tends to work for expectation values of observables, which we can use the estimator for in runtime, for example. If we have an unmitigated value, for example, such as, say, for example, variational quantum eigensolver, but this will work in a lot of cases, is we know the lowest value is going to be, the lowest value that we can get out is going to be the best value we can get out. So if we know some exact value is lower than the value we obtain in the green in an unmitigated way, meaning we just run the circuit and we incur the errors that we expect to run, any of those errors are going to have the effect of making a value that is above the exact value. And so knowing that, we can seek to minimize the value that we can obtain. So if we have an unmitigated value, which is a certain distance above the exact value, we can think about amplifying the noise in a scaled way and obtaining higher and higher values of that expectation. Doing this in a controlled way, being that we know how we're amplifying the noise, we can put that into a model and then scale that model back to the case where we've scaled the noise to 0 so that we get a mitigated value in the limit of no noise, which is closer to the exact value. This is how zero noise extrapolation works. And if you look at a paper that is just coming up from my colleague Redigit, we talk about an analysis of how to understand Z&E and the effects that we can have in running Z&E, because there are some options to choose from. So for example, there are different kinds of folding. Digital folding, for example, is going to mirror the circuit in such a way that you amplify the noise, versus analog folding, where you're actually scaling the length of the pulses that are being applied to implement those gates. So in this way, in the global folding, we're adding the inverse of the circuit and then redoing the circuit. So we've, in effect, in some way, scaling the noise by a factor of 3. But we can also consider doing local folding, where we're just going to scale the gates in such a way where we're going to undo each individual gate in a serial way instead of a global way. And often is the case, we're actually only going to do local folding to the noisiest or C0 errors or C0 gates that we have in the system, because we can approximate the single qubit gates as noiseless as compared to the 2-qubit gates. So these are kinds of strategies that you want to take into consideration when doing zero noise extrapolation, and Redigit's paper will help guide you in that. Some other things you need to know perhaps is how much do you scale the noise. So for example, this might depend on a couple of things. One of them is the error probability that you have given to you by the actual device that you're running on. And so if you look at the error probability on the left, given in terms of 2-qubit error, and the depth of 2 qubits on the right, this gives you a sense of how long, how deep of a circuit, and how much error you're scaling with. And in that case, the error models are going to be different. For these noise factors, which are relatively large, of 1, meaning no added noise, 3 times the noise, and 5 times the noise, we're able to analyze and see which function is able to fit that noise model and give the best expected answer. Here we have L for linear filter, Q for quadratic, and E for exponential. So that means these are all working in order to give a better value than you could get otherwise. But this no fit area given by NF is where this technique breaks down. So of course the technique will break down if you have too much depth and error has been accumulated, or if you have too much 2-qubit error and it's been accumulated as well. But you want to push this as far as you can. And you have also the cases where you could consider, if you had less noise, you could get away with possibly doing smaller noise factors in which you could have more resolution and you don't have to add as much noise per the system. So if you're able to scale that down and do these smaller noise factors, the linear extrapolator tends to work much better and the no-fit region is a lot smaller. So these are the kinds of things that you need to consider when doing zero noise extrapolation, on top of the fact that this roughly scales in quantum resources with the number of noise factors that you are actually applying. In that way, it's quantum mechanically slightly more expensive because you need to run more circuits to analyze them. So if we're looking at, say, for example, a Trotter step of quantum simulation, similar to my colleague Youngsuk with the polytwirling example, we can consider what the correlated z values of an expectation value would be, where the light blue is the ideal one and the purple one is the no mitigation is applied. And then z and e is going to give us some improved result, but not quite to the maximum that we could get in the light blue. The other thing about z and e is that it can be invoked using resiliency level 2 in Qiskit runtime. That's also where you can specify details such as the extrapolator and what kind of folding you would like to do. And then finally, probabilistic error cancellation seeks to do something a little different. What we're going to do here is we're going to try to learn the noise, these gammas, which are our noise models. We're going to try to learn them by doing polytwirling over the circuit into different layers so that we can learn what the noise channels are, and then we can effectively invert them. Now this isn't always a physical thing to do. You can't always invert this matrix, but you can try to do as best as you can, and that's what probabilistic error cancellation tries to do. However, you must run many, many, many circuits to learn all of the layers to then apply your probabilistic error cancellation, so this can be an expensive technique. But if you are able to do it well, then you can look at this Trotter step that we saw in the last one, and you can get very close to the expected results, meaning the dark blue is now on top of the light blue. So you're getting much closer to the expectation value that you would like, and that comes with Qiskit runtime resilience level 3. And you can read about that more from my colleague Ewout, who talks about that in this paper down here. So putting this together, we want to think about what can we actually do with a quantum computer in some amount of time, given the resources that we have in terms of how many circuits we can run, the time they take to run, and overall errors. So we define something we call runtime J. My colleague Sergey has written about it in this paper below. And we have a few variables in here we'd like to put together. So first of all is the depth, which is like the depth of the circuit. How many layers do you have? And so that's going to affect how long it takes to run. We have this value called gamma bar, which you may have heard about. This is a very important value, and it's related to the overall error. In fact, gamma bar is equal to e to the 4 lambda bar, where lambda bar is kind of an average error of the quantum device. So this is something you have to characterize if you really want to understand what you can do with a quantum computer given a certain amount of resources. In this case, it's the depth and error and number of qubits. Speaking of number of qubits, that's what n stands for, because the amount of error you have, you're going to suffer from errors on all of those qubits. That's why gamma bar is raised to the d times n power, where then beta is your average layer execution time, which is given by the speed of kind of how many executions can you do per second. This is characterized by a metric called CLOPS, or circuit layer operations per second. If we multiply this all together, we can get the actual runtime of an algorithm J in terms of these error mitigation techniques. And putting it all together, what we are trying to achieve is we're trying to use error mitigation in order to extend the reach of noisy quantum computations to be able to do something useful, meaning beyond that of a classical computer. But before we get to the era of quantum error correction, which is defined by a fault-tolerant quantum error correction regime, where you use a number of physical qubits to implement a logical or fault-tolerant qubit. which is often the future. In this way, we have posed a challenge called the 100 by 100 challenge, in which we are wondering what are the kinds of problems that we can solve in one day that are of depth 100 layers and 100 qubits. And we think that just trying to see what can be explored on a reasonable timeline for people, one day, and a reasonable number of qubits, 100, and a reasonable depth, we think will be a very interesting challenge for the future. So we invite you to think about how you would implement this, and hope you appreciate the outlook on quantum error mitigation and suppression and all the techniques that we are developing. I'm sure they're going to be extended, and I thank you very much for paying attention, and I hope this has a positive outlook on you running your quantum circuits. I've been your host, Nick Braun, and thanks for watching.